Tá vendo a tela?
Sim.
Vocês conseguem ver meu cursor também?
Bem. So welcome everyone to today's seminar. Today, it's a pleasure to have Camila Novais, who is a recently appointed researcher at INPE, and she's going to be talking about simulations, from simulations to cosmological constraints, a machine learning approach. So Camila holds a bachelor's degree in physics from INPE, in Itajubá, and then a master's and PhD in astrophysics at INPE, the institution she is now. Her research field focuses on observational cosmology with emphasis on data analysis of the cosmic microwave background and its anomalies, as well as 21 centimeter cosmology and other large-scale structure tracers. Camila, thank you so much for accepting our invitation. The floor is yours when you're ready.
Thank you, Anna. Thank you for the invitation. It's super nice to be here with you remotely. So the idea of the talk today is just show you a new but not that new approach to constrain cosmological parameters now through simulations, and more specifically using machine learning in the middle of the waves. But I will explain what I mean by that. So I will start just with some introduction and motivation for the statistical tools that we use. And I will present some examples. I will spend most of the time in this first example, analyzing weak lensing. And then I will show similar analysis, but using different large-scale structured tracer, and also using CMB data. And then the conclusions. So just to start, sorry. Yeah, so just to start, in cosmology, we usually say that the seeds to the large-scale structure, they are their origin in the early universe are mainly are basically an stochastic process, so that we cannot say where a given object, a given galaxy, for example, is coming from in the early universe. So we cannot trace it back to the early universe, but we can predict how they are clustered. I mean, how is their statistics? How we can do this? We usually do this using 2-point statistics. You can use, for example, 2-point functions in real space, where I show this example here in this plot. And we can also use the 2-point function, but translated to the harmonic space, where we see here the angular power spectrum, which is very commonly used for CMB data analysis. And here and here, these two plots show the 2-point statistics, but in the Fourier space. So this is for a long time we have been using these statistics for a long time now to do cosmology, and our traditional way of using them to do cosmology and to infer cosmological parameters is summarized very briefly here in this slide. So from your data, you can extract these statistics, these 2-point functions, any one that you prefer, and then you can use, for example, a Boltzmann code, for example, CAMB or class, to predict which would be your 2-point function. Then you compare the 2-point function that you extract from your data to the theory, to what you expect from theory. And to do this, you use some Monte Carlo Markov chain method. This is basically Bayesian analysis, and then the best fit parameters at the end will be your constrained parameters. So, but to do this, usually in most of the analysis, people usually consider a Gaussian approximation for this likelihood, for the likelihood of your data. But not always this is true. Actually, when you are analyzing CMB, you have a temperature fluctuation field where you can approximate by a Gaussian. But when you go from CMB to study a large-scale structure, you are not you don't have a Gaussian distribution of resources. Very different. Actually, it is very different from it. It's more log normal than Gaussian. So it's complicated. Just assume that your likelihood is Gaussian. Just an example, here we have two maps from a given large-scale structure tracer. Here in this first plot, you have a Gaussian distribution and of this tracer, and in the second map, we have a non-Gaussian distribution of the tracer. And you can see here that when we extract these two-point statistics, here specifically the angular power spectrum, which gives you the amplitude of the clustering of that tracer according to the angular scale. Here we have larger scales, and here we have smaller scales. So we can see here that both of the maps, Gaussian or non-Gaussian, they produce the same two-point statistics. So to go to extract the whole information, all the information that this field can provide you, you have to go beyond the two-point statistics. So as I showed you before, this is our traditional inference analysis and how we could go beyond the two-point statistics. For example, substituting this theoretical calculation of your statistics by an emulator. But why we need an emulator here? And we cannot just plug a class code, any Boltzmann code like to calculate these non-Gaussian statistics. Here you can see a list of them. I am not going to the details, but each of them, with different colors, they are what we call higher order statistics or non-Gaussian statistics, where you have not only the two-point information, but you go beyond. You have more information than in the two-point information. But the problem here is that you don't, in general, you are not able to model these non-Gaussian statistics theoretically. So you don't have an analytical expression for the likelihood, for example. So people usually use this emulator. You can produce many simulations for different values of your cosmological parameters, here represented by theta 1 and 2, so that you can emulate how your non-Gaussian statistics would be when you change the cosmological parameters. So you can, after that, again, consider a likelihood. In general, again, Gaussian, use this MC method and then infer your cosmological parameters. So here, instead of just comparing what you have from the data with the theory, you are comparing with what your emulator is providing. So how can we go even beyond this and avoid assuming any likelihood, any format, any assumption for your likelihood? You can, for example, use this approach called the simulation-based inference that you will probably see with find it with other names like likelihood-free inference or implicit inference. And the idea here is the same. You have here your data, and you have the statistics that you can calculate from your data, and you again have to simulate your data, and the simulations should be as close to the data as possible, so that your machine learning here, your neural network in this case, can learn which is the dependence, which is the relation between your summary statistics and a given change in your parameters. So the idea here is that the method will learn what a given modification in the cosmological parameter, what this will cause in the summary statistics. And after your method learns that, you can apply the trained model to your data, to your real data, and you can this way constrain your cosmological parameters. And you can use this approach for any kind of data. As I showed you before, as I mentioned before, I will show you these 3 different examples. So I will start with this example using weak lensing, showing you results from a last work that we just that it was just accepted and published. So just an introduction to this and a motivation of why we decided to do this kind of analysis and study. We have here in the middle a simulation of the distribution of the dark matter. We cannot directly observe the distribution of the dark matter, but we can observe the tracers of the dark matter. For example, here I mentioned the 21 centimeter intensity mapping that will be related to how this dark matter is distributed. In the same way, we have the galaxy clustering and also the weak lensing, where the light from your galaxies in the background are distorted by the presence of massive objects along the line of sight. And you will have this kind of data, but I will mention what this is. So in general, we have 2 regimes for the gravitational lens. The strong one that I show here in the left. So if we take a look in this other figure here, we see that here we have a very massive object which is distorting the light from the galaxies on the background. And you see that here we have a strong lensing effect. But in general, for cosmology, the weak lensing is even more interesting. So if we zoom in a small patch of this region, which is far from this massive object, we can see this other figure. And if we just see this figure, we cannot say that they are, for example, lensed. So how can we measure the lensing effect and check if, in fact, there is this lensing effect? When we measure, when we see this kind of figure, what we measure actually is the ellipticity of each of these galaxies. So we measure for each of these galaxies its ellipticity, and if we take the average ellipticity of all these galaxies, we will find something along these black lines here, which is tangential to this massive object. So which is the point here? So it's not that simple. because when we measure the ellipticity of a galaxy, we are not only measuring the ellipticity because of the lensing effect, but we are measuring the ellipticity that includes the intrinsic ellipticity of the galaxy, because when you see a galaxy, you see that it is elongated, so it has already an ellipticity. And you will see, and another factor is this shear, this gravitational shear, which is the signal that we are interested in. The ellipticity, because introduced by the lensing effect, the gravitational lens. So also we have to consider some bias effect to take into account other things and systematics that we are not aware. So after we can finally measure this shear effect, which corresponds to just 1% of all the signal, we have this mathematical expression that we can use to transform the shear signal to the convergence signal. So what you see here is a map of the convergence of the galaxies, where the red spots will be the regions where you have more mass, and the blue ones will have less mass. So this is basically a projection of the distribution of matter along of the line of sight in a given redshift beam, for example. So, but why is interesting, and what can we learn from this convergence map? For example, we can perform analysis and estimate omega m, which is your matter density, and your sigma 8, or a combination of them called the S8, which basically give you an amplitude of the clustering of the matter. And you can see here from this equation that the convergence is directly related to the density of the matter. So you can relate it. It can provide you information about this density of the matter, and also from this sigma 8 parameter. And a combination, we usually constrain this combination of the two parameters because they are degenerated. So this expression here is used because how they are degenerated, how is the dependence of the two parameters. But why is that interesting to constrain this S8 parameter? I showed you this plot in one of the first slides, and we can see here many measurements from the CMB and also from large-scale structure tracers. You can see here these measurements of the matter power spectrum, which corresponds to how the matter is clustered according to a given scale. Again, here you have large scales, and here you have small scales. And when you take each of these measurements and just zoom in the amplitude and estimate these amplitudes, you can plot your S8 parameter, your S8 value for each of these data. So you can see here from this plot that when we take a look in the measurements from early universe, from basically CMB data, and when we compare them with measurements from the late universe, from large-scale structures, tracers, we see that they are not totally in agreement. This is what we call today the tension in the S8 parameter. And what is interesting here? Why we want to understand why they are different, why they are in tension? Because to go from the beginning of the universe, when you had this release of the CMB, to the late universe today, you have many things happening here. You have this growth of the structure. And this growth of the structure depends on many aspects of the universe. The expansion, how gravity acts, and the composition of the universe. So by studying this tension and why this is happening, you can learn many things about the universe. So let's go to the analysis. Here, our idea is to estimate omega m and S8 using higher order statistics. And for this, we use the first year release of the Subaru Hyper Superchem data. This data is basically coming from 6 different and disjoint patches of the sky. Each of them are showing you the convergence of that patch. And here in this table, you can see the slices of the redshift that we are considering. This last one here, people believe that they might be contaminated with unknown systematics, so we don't use it. We are then focusing on these 3 redshift ranges that I put here. So this is the team with who I have been working with. They have developed different works using different non-Gaussian statistics. I put the name of each of them here. But I have to call your attention that all these analyses have been done using that emulator, as I was explaining in the beginning. So here we are not still using neural network or simulation-based inference. We are, I am part of some of these works, not all of them, but all of these works use the simulator approach. So the difference from all these works to the one that I am showing you today is that instead of using the emulator here, we are plugging this neural network to do this link and provide the inference of the cosmological parameters. So how exactly we are doing this? I will, this is a summary, but I will explain each part of the pipeline. So we start here with the simulation from a given value of cosmological parameters. We vary these cosmological parameters so that we have many simulations for different cosmological parameters. And we extract the summary statistics, we do some compression, and then at the end we will do these inference of the cosmological parameters. But the main thing here is that you can see that there is 2 parallel lines showing that anything that you do with your data, you have to do with your simulation, because your simulation need to reproduce what you see from the data. Because if not, your machine learning method will not be able to recognize any pattern. So let's start with the simulation. As I mentioned, we need many simulations, as much as we can. Here we are considering 100 different pairs of cosmological parameters. And so for each of these red dots representing a pair of parameters, we have 50 realizations, 50 simulations of the 6 patches of the HSC year 1 data. And we have an additional set of simulations, a larger set of simulations that we call fiducial, that we don't use to train our model, but we just use to test. And again, I would like to call your attention because all the simulations have to reproduce what we see from the data, which means we have to consider the same geometry, the same area of the sky, how the galaxies are distributed in the sky, and many other characteristics that we can get back to it if you'd like to ask questions. So after we produce our simulations, we are then going to calculate the summary statistics. Here, we considered 4 different summary statistics. One of them is the angular power spectrum, a Gaussian statistics, very commonly used, as I told you before. And we use 3 other non-Gaussian statistics. The peaks and 3, but 4 actually, because you have the peak counts represented here with these graphs, and the minima counts, which is basically you can for each pixel of your map, you count how many pixels around it that has a higher amplitude or a smaller amplitude. So you can just count. And the Minkowski functionals, where you have 3 different Minkowski functionals, the area, perimeter, and the genus, which basically give you information about topology of your field. Again, I'm not going to the details here, but we can get back to it if you are interested. And the last one is the probability distribution function, which is basically histogramming the pixels of your convergence field. So we are using all these statistics. We test each of them individually, but the idea is to combine all of them. So if we take a look here, we will see that we will have many statistics, each of them calculated for different values of the convergence or different values of the multiple. So each of them corresponds to a data vector, which is big. And when you combine everything, you will have to deal with data vectors which are very long. So how we deal with it before doing the constraints? We do this data compression. To do this data compression, we use a neural network. Basically, here again, we have we choose our cosmological parameters, we simulate the cosmological fields, extract the summary statistics, and then we will give the summary statistics and the corresponding true values of the cosmological parameters. And then this neural network will learn the relation between them. So it will learn what happens with the summary statistics when I change the cosmological parameter. The idea here is that after the neural network learns this relationship, you can give another set of simulations or even your data, and from the summary statistics calculated from your data, it will be able to predict the cosmological parameter based in what the neural network learns. So I here put just the size of the data vectors that we are considering if we combine all the statistics. So this is a very large vector. So in order to go on and use the last step of our pipeline, we have to do this because this SBI in the end does not deal very well with very long data vectors. And just one comment here, we didn't do this, but a possibility is just go from the cosmological fields directly to as an input to a neural network. In this case, you use a specific type of neural networks called convolutional neural networks, where you don't have to extract your summary statistics, but your neural network will extract the summary statistics itself. Okay, então, then these here are the results of the compression, or we can also call the prediction. So you have here a comparison between your true value, because we're talking about simulations, then we know which is the value of the cosmological parameter, with the predicted value, the value predicted by the model, by the neural network after it is trained. So you can see here in each color the result produced using different sets of summary statistics. The blue one is using just the angular spectrum, while the red one combines the Gaussian statistics and the three non-Gaussian statistics that I listed before. So you can see clearly here that here and also in the results for the I-safe parameter that the red points and the error bars, they are more close to this diagonal than the blue one using only the angular spectrum. So basically we have an improvement of the error, of the uncertainty of these parameters, of the constraints of the parameters of 30% for omega m. And we have an improvement of 21% when we consider Gaussian and no Gaussian statistics instead of using just the angular spectrum, just the Gaussian statistics in blue. Okay, so this was the data compression part, and now we go to the last part. This last part takes as input the compressed data, your prediction from the previous step. So after you compress your data, your summary statistics, just into two numbers, you can use this neural density estimator, which is basically another neural network which will learn the relation between this compressed data and the true values of the cosmological parameters. So here, this neural network will compare the both of them. And the idea here is that it will learn how this data is distributed, which is the likelihood of the data. Actually, you can use different neural density estimator. For example, one that will learn the likelihood of your data. So this would be a neural likelihood estimator. But here we used a neuroposterior estimator, where the method, the neural network, will learn directly the distribution of your posterior. So after training your NDE, your neural density estimator, you can apply it to the predicted values, to the compressed values coming from your data, your real data. And then applying this trained model to the real data, you can infer you can infer which is the posterior distribution of your data for each of the cosmological parameters. Okay, so before going to the results, to the constraints we have for omega m and S8, we first have to be sure that our method will not produce any biased result. How we do this? Because we think that we understand the data and know what the data have, but the data may have some systematics that we are not aware of. So, for example, this plot here shows the distribution of the redshift of the sources producing this convergence field. And depending on how you calculate the redshift of the sources, you have a different distribution of redshift. So what happens if I train my model with simulations, and then I discover that then at the end, your data is not following this distribution, but it is following this other distribution. So to test that, we produce simulations following another redshift distribution and then apply the trained method to infer the cosmological parameters. And we do the same things for other three different possible systematics, like a miscalibration in those bias that I showed you before, the bias on the equation of the electricity. And also we consider what happens if you are considering this baryonic feedback and also intrinsic alignments. So we test all of these and we decide which is the exact pipeline that we are going to use based on that. So here we focus in this one here where we compare everything, we combine everything, all the summary statistics. And when we apply our trained model in a new set of simulations, including these systematics, we see that the bias introduced in the S8 value is not larger than 0.17 of the 1 sigma deviation of the obtained from the simulations. So here you can see as black dots the results, the S8 estimated for each of the cases and the 1 sigma deviation. And in blue, in gray, this gray region corresponds to this 0.17 sigma, just to show you that the bias from in any of these systematics will be inside of these regions. And this is how we define our pipeline, like the scale cuts and the smoothing scales and other characteristics of the analysis we choose in such a way that we don't increase this bias. Okay, so this is the results from the data. So we have here the constraints from each of the combinations of statistics. In blue, just the angular pi spectrum. In green, only the non-Gaussian statistics, the peaks and minima, Minkowski functionals, and PDF. And in red, everything combined. So you can see here from the S8 parameter in particular that including or not the CL, I mean, comparing red and green, you have very similar constraints. So the most of the constraining power here is coming from the non-Gaussian statistics. Here we can also compare, the first three are the results that I just showed you in the previous slide, and the other results are coming from using each of the summary statistics individually, and each of them combined with the angular pi spectrum. And here you can see the inferred cosmological parameter, S8 parameter, and the corresponding error bars. And you can see here in gray the region corresponding to this first point here, which is our baseline analysis, our main result. And in parentheses, you can see how this result is better than the result obtained just using your 2-point statistic. So you can see here that the main driver of this improvement is the Minkowski functionals. So here I put the constraining power of the 4 non-Gaussian statistics. Okay. And here a summary of of our results from our team, and the results coming from analysis of other sets of large-scale structure data, and also using non-Gaussian statistics. So you see here in red those results that I showed you in one of the slides where I showed the team. And this one here is the one using this SBI approach, where we don't assume any any shape for our likelihood. So just to summarize our findings here, first, we could show with this analysis this robustness of the pipeline against systematic effects. We confirm this high constraining power of non-Gaussian statistics compared to the Gaussian statistics, to the angular power spectrum alone. We also see that is relatively easy to combine several statistics, like we did here, combining Gaussian and other many non-Gaussian statistics, and we didn't have to do any approximation, so we can think here in how would be to construct, for example, a covariance matrix for all these statistics combined. It would be very difficult. And finally, we can see from these results that the SBI seems to be very competitive and feasible, even with this limited number of simulations. What I mean here, this pipeline will work better when you have many simulations. And for weak lensing, the simulations than any other kind of simulations actually, but in weak lensing, simulations are usually very expensive. So even using just 100 different values of the cosmological parameters and just 50 of realizations for each different value, we could achieve and estimate very well the cosmological parameters. Okay, so this was my last slide for this first example. So based on that, I will just mention quickly about two other examples of where we can use and where we have been using this approach, the simulation-based inference. For example, for intensity mapping, for 21 centimeter intensity mapping specifically, where we basically, for this tracer, we basically are measuring how the hydrogen is distributed. And since the universe has hydrogen until very high redshifts, we can map the universe until very high redshifts. And we can apply very similar methodology to extract cosmology and constrain cosmological parameters from this kind of data in the future. So here, using simulations, we show how this simulation-based inference is seems to be very nice option, alternative to traditional analysis, also in the case of 21 centimeter. And the last example is the CMB analysis. I will just mention this first work where we used a very similar approach, but to estimate the amplitude, this FNL here is the amplitude of the non-Gaussian signal of the CMB, which we and many other works discovered that is approximately Gaussian. But to do this, we need to use non-Gaussian statistics, and we do this in these works 10 years ago. And but what about future experiments? When we think about future experiments for CMB, we automatically think about measuring the B modes, if they exist. But just to give you an idea of how difficult it will be to measure these B modes, we have here, again, the angular power spectrum, theoretical, calculated for the B modes, and when you have here in orange your cosmological signal. So to measure your cosmological signal here for different values of R, R is the tensor to scalar ratio, which is directly related to, for example, if you measure this parameter to be different from 0, you are saying that you are measuring the B modes, which means that you are checking, that you are verifying that there is primordial gravitational wave. So to get to your cosmological signal, you have to get rid of the contamination, the foreground contamination from astrophysical sources, and then you can see here how they are. They have a much higher amplitude, and also the lensing effect, which converts part of the E mode into B mode. But in terms of future experiments, another very interesting thing to do is also measure the E mode. Because if you take a look in this table here, which comes from measurements from Planck collaboration, you can see that this optical depth of the recombination, you'll see that this reionization, you see that this parameter is the less constrained from all the basic lambda CDM parameter. So in the future, with this CMB much better this parameter, and as a consequence, we will also be able to help understanding, for example, the S8 tension that I mentioned before. So just to finish, here is an investigation that we are doing now. We are simulating two different future surveys of the CMB, Lightbird. Both of them are satellites, so they measure from outside of the Earth. And Lightbird is already under construction, and Pico is not accepted, but as far as I know, is almost accepted to be constructed. And here, I just would like to show you that besides the astrophysical contamination, we will also have to deal with instrumental contamination. Here, the noise of the instruments. So you can see here which is the level of noise of Lightbird and the level of noise of Pico, and you can compare the cosmological signals for different values of R and tau. The amplitude of these systematics compared to the amplitude of the cosmological signal. So it will not be easy to do this. And again, we can follow a very similar pipeline where you can construct simulations of the E and B mode maps. We can extract the angular power spectrum after cleaning all the contaminants, and we can plug this angular power spectrum, this 2-point information, in a neural network so that we can relate it to the cosmological parameters that we are interested in. And here are the preliminary results by doing that, where we compare the true values of the cosmological parameters and the predicted values. And we can see here how well these two instruments will will constrain the two cosmological parameters through this kind of pipeline. So I will just finish here because I think I reached the time. But just to finish, I would like to show you this figure. It's not up to date, but can show you the many instruments that are taking data and expected to take data in a near future. And for this next generation of surveys, will be particularly beneficial by this kind of approach, the SBI approach. And it would be a easier way to combine summary statistics, also not only from the same probe, but from different probe, for example. But we have to be realistic because it's not that easy, because we need simulations, and we need your simulations to be good enough so that our pipeline, our method is trained efficiently, because without simulations, there is no simulation-based inference. And I will finish here. Thank you.
Questions? Okay, whoever, just.
Hi, Camila. Thanks for the talk. I saw that you showed the comparison of the systematics from the feedback, baryonic feedback, right? First, did you test this with different subgrid physics, or you assumed a specific model for the baryonic feedback?
Yes. In this case specifically, we use a simulation including baryons, this baryonic feedback, following a given model. And we then calculate the same summary statistics from the same simulation, but without the baryonic feedback, so that we have the effect directly in the summary statistics. And then we introduce these expected results from this model directly in the summary statistic. Was that your question?
Yes, yeah, part of it, but when you use the hydrodynamic simulations, there is different flavors of this baryonic feedbacks. So did you use a specific one, or did you test different subgrid physics?
Yeah, unfortunately, I cannot answer completely your question, because I didn't work directly in this part. But as far as I know, we consider just one, as you say, flavor of this,
Okay,
not
thanks.
different ones.
Yeah, okay, thank you.
Miguel?
Oi, Camila.
Oi.
In the first example, I see that the noise is pretty low, or the signal is low. Did you handle the noise for that observable?
Which noise you mean?
No, the signal in the first example.
You mean the weak
spectrum.
lensing, right? You mean this analysis with using weak lensing?
Yes.
Okay.
Can you go back? You have
Back.
a plot of the angular power spectrum that you make in the simulation. It was around.
I think you are talking about maybe the CMB, not weak lensing. Let me show you, and you say that.
Okay, which slide?
I don't remember the slide, but was it a fair example? Go back.
Back?
37 back, 30, 20 or something.
Around 17.
Good.
17.
There we go. There you go. Yes.
Yeah. Now go further.
Okay.
20.
Well, my first guess was right.
Okay.
That one. No.
Which one?
22. That one. In the left corner, you have those signals.
Here, you mean peak and minima counts?
No. Up.
The angular
Here, the angular power spectrum.
So the signal is around 10 to the minus 9.
Yes.
How do you handle the noise for that signal?
The noise, you mean
Shot noise or
the shot noise appearing is mainly for larger multiples.
but you have larger multiples right there.
Yes, but we cut. We actually use only these 4 points here. We cut the first multiples, and we cut also, we don't consider these larger multiples. We just consider this part here, these 4 bands of multiples.
But usually the signal is more contaminated as the multiple grows. So
Exactly.
for me, those are larger multiples, so should be biased by the noise.
By the noise, you mean shot noise,
Yes.
due to the number of galaxies and yeah, as far as I understand, the shot noise acts more in this region. And yeah, indeed, these are larger multiples. But yeah, you're right. We have to be sure that this noise is not biasing our results. So we apply a smoothing scale so that we cut even more the larger multiples, the smaller scales. And we tested different smoothing scales, and we found that a smoothing scale of 4 arc minutes would not bias our results. So this smoothing procedure will probably take into account this noise appearing here.
Okay, and what about the mask of the survey?
Yeah, here you have 6 regions, and you see that not all of them are very well behaved. You have some cuts here and cuts here.
And when you do the simulation, you do it in those redshift range that you showed there.
Yeah.
Do you take an effective redshift, or do you vary the redshift continuously for making the simulation? The simulation.
Yes, we have to check which is the distribution of galaxies with redshift inside each of the 3 redshift beams, and we produce the simulations in such a way that the galaxies in the simulation will have a similar distribution of galaxies inside each of the redshift beams.
Okay.
Maybe we can continue to see if there's more questions. Are there questions from Zoom?
I have one.
Okay.
Or 2 actually. So Camila, first, thanks for the talk. I had to miss a bit, so forgive me if I'm asking something that you explained, but I'd like to bring 2 generic questions just to get your opinion about that. I think it's really good to use neural nets to approximate distributions. Of course, they are very powerful, and we could do that with other simple things like Gaussian mixture, but they are efficient. But there are 2 critical points that I just like to hear your opinion. One is how to guarantee from the information theoretic viewpoint that the summary statistics is a sufficient statistics. Because that's a general problem of compression, right? And especially if you are combining different probes. And the second one is, given a limited amount of simulations I can run, it's not optimal to just run irregular grids. So did you think about how to make it, let's say, an optimal sampling from the grid of the simulations via maybe active learning or something else? Is there anything that you are thinking or already considering now or in the future? Because these are 2 problems that we are going to face always, right?
Yeah. So just to be sure that I understand your question, you mean how I am sampling the parameter space like this with these red dots?
Yeah, because exactly that's the optimization problem, right? If I have a limited amount of resources, how do I sample in an optimal way?
Yeah, in this case, I don't think we consider this, but we can use, for example, these methods, Latin hypercube that's very commonly used. But in fact, this is important because since these simulations are super expensive, we have to choose very well these parameters. But yeah, I would choose this Latin hypercube, but I am not an expert on this. I know that it's the most commonly used, but I think there are others, right?
Yes, some groups they are trying to plug active learning because it's kind of learns from the like you can plug in as a feedback loop. You sample in a particular region, then you check, and then you learn. It's similar to population Monte Carlo because
I
it basically creates generations of samplings, and then you get smarter. So that's
uh,
one option. I know some people in some groups in France and UK they are doing that. So it's just something that you might consider.
yes, for sure, but I have never used this, and I'm not that familiar, but I would guess that this is more expensive, right? Because
Well, I mean, depends. It learns initially you'll be as dumb as regular grid, but with one, two, or few interactions, it gets optimal.
I see, then you wouldn't need that much
Yeah,
simulation.
it's like if you have a genetic algorithm just to teach you how to do the sampling, something like that.
Yes, yes. Yeah, this is very interesting.
And about the summary statistics and the sufficient, how do you? How that's another issue, right? How do I say? How do I know I'm encoding the data in an optimal way?
Actually, well, from my opinion, we don't. We just test many of them to check which would be more appropriate. And from our analysis, testing only these summary statistics, what we see is that the Minkowski functional seems to be the best one.
Okay, thank you.
Thank you.
Okay, because we're already past 1:30, if anybody has questions, you're welcome to email Camila. I'm sure she's gonna be very happy to receive your question. So to finalize, let's thank Camila again.
Thank you.
Thank you.
Thank you.
Maybe sometime we can meet in person.
Yeah, I hope so. Thank you all, and
Thank
thanks for
you.
the invitation. Bye bye.
Camila,
Yeah.
Oi, Camila.
Miguel is gonna continue.
Oh, yeah.
Agora eu falo mais para que fique mais tranquilo para falar assim. Só para entenderem no processo se eu troco a cosmologia, em que parte do processo que você mostrou vai afetar o resultado, ou posso trocar